Hello everyone and welcome to the solutions for Codeforces Round 777. That's one number. So I'm going to be discussing A to D because that's what I solved. And with that said, let's jump right into it. But before that, make sure you have subscribed because if you don't, what are you doing? Subscribe. Okay, that was a very bad plug. I will lose subscribers by that. So problem A. In this problem, we have to generate a number which has the sum of its digit equals to n, and I want it to be as big as possible. Now if you want a number to be big, the more digits it has, the bigger it would be. So the best number would be 1 repeated n times. However, there is a constraint that no two digits can be occurring in this no two digits can occur twice in a row, and also we cannot use 0. So I cannot have this. I'm gonna have to do something like 1 2 1 2, because see, the more digits I have, the better answer I would get. So something like this, or maybe this would be the best option, because this will give me the most digits in least sum. And now we want to make sure which one is bigger. So either of these I will pick and take the bigger one. But what is the proof that these two forms of numbers will always give me any number? So I want the sum of digits to be exactly n. So I just need to make sure that the sum of digits of numbers of these type 1 2 1 2 and 2 1 2 1 is always enough to cover any number n. So let's analyze a number like this, which starts with 1 and ends with 2. So there are, let's say, x1s and there are x2s. So it will cover all the numbers that are divisible by 3. Let's say it ended with 1. So it will cover all the numbers that have a remainder of 1 when divided by 3. So 3x and 3x plus 1 are covered. Now I just want 3x plus 2 to be covered. So let's see, 2 1 2 1. Now, and it ends with 2. Okay, so if it ends with 2, then it is 2x. Let's say they are x, right? And then there would be x minus 1 once. So there are x 2's and x minus 1 once. So that is 3x minus 1, which is equivalent to 3x plus 2. So we can always cover every number. So these, I just need to figure out which one of these first of all is able to get to a sum of n, and then take the one which is bigger. So let's have a look at the implementation. So for the implementation, I used a solve2 function, which for a given x and a given starting point x will generate the string, which is answer. So while n is greater than 0 and n is greater than equals to x, what I'm doing is, let's say I start with 1. So I will add 1, then 2, then 1, as long as n is greater than equals to whatever we need to add. So if it is 5, I would add 1 to 1. But notice that I would not be able to add 2 here. So if I'm not able to add 2, that means n is not 0 now. That means I cannot do it. So can is false. Now I generate the two strings that can be the output, one that starts with 1 and one that starts with 2. And then I know that if one of them cannot be the possible answer, then the other will always give me the answer. So these two lines, and then uh, I need to pick out the bigger one. If both of them gives me the answer, which one would be the bigger? One which starts with 2, right? So that is simple. The one that starts with 2 would be the one for which starting number was 2, so 8. So that was the solution for A. Now let's have a look at solution for B. So In this we are given a bunch of terminology. So we have a grid of n by m. Let me just draw it real quick. And now there are zeros in one. Now ones can be like this. So 1 1 1 1 1 1 1. Now we are told that let me just show you here that something so a subrectangle is okay. What's the first one? Yeah, so a subrectangle is black if there is no zero inside it. So the ones that have one inside it, all those cells, those are black. Now a subrectangle is called nice if it is black and it is not contained in another black subrectangle. So oh, okay, I don't need to show that. So notice that this, what is this? So this is a subrectangle, right? This is a black subrectangle because it has only ones and it is a rectangle. But notice how it is totally devoured by the other subrectangle. So this is not nice. And this is also totally devoured by this one. So in conclusion, this is a nice subrectangle which cannot be further devoured by anything else or totally covered by anything else. And then there is a term called elegant. Now a table is elegant if all the nice subrectangles, so all the biggest subrectangles possible, those do not intersect. Now see that there is another subrectangle here, another nice subrectangle, this, because no other subrectangle can totally completely cover it. So we have these two, and now notice that these two are intersecting, so this table is not elegant. So with that, now you can see what is the condition for a table to be elegant. Now for a table to be elegant, am I recording? I am, right? Yes, okay. So for a table to be elegant, what we want is all the subrectangles to be isolated. So all the nice subrectangles, so which are black and also non-intersecting, all of them to be present in a disjoint manner, so none of them intersect each other. So this is what I need to check. Everything needs to be a subrectangle and none of them have to intersect. So that's pretty simple. And now you might be thinking, well, what if it is something like this? So these are the ones, but there are zeros inside here. Will this be an elegant table? Well, it won't be, because I have one subrectangle like this and one like this, nice subrectangle, and there is intersection. So in all cases, I want subrectangles to be completely filled and completely disjoint. So that is what I need to check. And now how can I check that? That was the main part of this problem. So to check that, I think there can be much more elegant ways to check it, but I did it in a very stupid manner. So how I did it is, I iterate from top left to bottom right like normal, and whenever I encounter a 1, right, so whenever I encounter 1, I'll go to the right and see how much to the right I can go. So I can go up to here, right? I can go this much. Now as long as there is, so I will now go to the next row, and now if this next row is completely zeros up to this column, so j to j2, if this is completely zeros, then that means this has been detached and it works fine. However, if there was some but not exactly j2 minus j1 plus 1, whatever, so if there was not exactly that much, so that means if j1 is this and j2 is this, so j2 minus j1 plus 1 is 4. If there were not 4 in this range in the next row, then that means some are missing, and those some which are missing will cause this to not be a perfect rectangle. And then also I will print no. and I'll keep doing this for as long as there is a subgrid. And also, if everything is red, right, so if this was also red, then I'll have to make sure of one more thing, that ones are not here, because then I will get another subrectangle like this. So I need to make sure of that. So just an implementational headache. Yes, I think headache is the best way to describe this problem. Garbage is another. I really did not like it. So I take the input and I have a visited, so that I do not visit any cell more than once. So I go from top left to bottom right. If something is visited, continue. If something is zero, obviously I don't have to. What am I doing? Yeah, I don't have to worry about it being nice or elegant. So continue. Now, first of all, I'm gonna find J2. Now J2, I was saying this, but J2 would basically be one more than the last cell with one, because I just wanted the less than inequality. So I iterate and find what is the J2. J2 means, so if in this row there are 1 1 1 1, this is J, then this is J2. Okay, so I find that, and now for the next row, I so I go from I plus 1 to n. I keep iterating on rows, and I count how many cells were 1 here. So if all of them were 0, so in this range, right, from J2 less than J2, if all of them were 0, then that means that subrectangle has been completed and I can break out, everything works fine. However, if it was not, so if it was not 0, and if it was not equals to this, so count was not equals to J2 minus J, so it was not 4, then that means it was something like maybe this, and again this would not give me a perfect subrectangle, so print no. And then I have to make sure that let's say it was like this. Now what if there is 1 here? If it is like that, then I'll get a bad subrectangle, a nice subrectangle which will intersect. So I have to make sure for J2, so AI to J2, and then I also have to make sure for this AI to J minus 1. And so I keep doing this. This is enough to check for a dense subrectangle, and if all checks passes, then print yes. Okay, so that was the implementation for problem B. Now problem C. Okay, so in this problem we have a grid again. I don't know why, but every time I see a grid problem I lose a lot of motivation. This is not fun, but this one was good. This one was good. So initially everything is 0, and I want to reach a final state. So initially everything is 0 and I want to reach a final state, something like this, right, where some are 1 and others are 0. And the operation that I'm allowed to do is choose a subrectangle, right, and then do chess coloring on it. So the first element would become 0 colored, second would become 1, and then this would become 1 0. So every time it starts from 0 and goes to 1, and the maximum number of operations I'm allowed is n times m. So this gives a big hint. Since we don't have to minimize, we don't have to worry about how many operations we are using, and since maximum is n times m, the big hint is that let's just try to cover every cell that is 1 separately. So if I were to try that, right, then how can I do it? Well, let's have a look. Let's say I wanted to color this. If I want to color this all black, right, and let's say it's like this, then I will have to first of all, and notice at every operation I'm trying to color only 1. So the order of operations would be, first of all do this subgrid, this will become 1, right? So right now, so this is the final state that I need, and the initial state is obviously everything is 0 6. Now I'm gonna why is this keep coming? So I choose this subrectangle, and the first goes 0, the second becomes 1, so this becomes 1, and then I choose the next one, this becomes 1, and the next one, and so on. And notice that for the last one I need something on the left or on the top, right? I either need it on the left or top so that I can do an operation and make it 1. So you saw that to get all these ones here, all I needed was to have a 0 either here or here, because then what I can do is, okay, this is getting really annoying now. Now with this what I can do is, first of all, use the cells inside of it to form the right ones, the bottom right ones, and then in the end I can either use this or this. So that means I need 1 0 to be present in the top left, right? So I mean at the left of the top left or the top of the top left. So this is the top left, right? So I want something to be 0 to be present either on its top or either on its left. If it is, then I can do it. And now let's take an extreme case. Let's take an extreme case where by the way, the observation we just made is also consistent with that if I wanted 1 here, I can never get it, because any subrectangle I choose can only at worst, at max, at best begin from here. And if that is the case, it will always be 0. So that can never happen. However, let's say my final state was, okay, my final state was like this. This is 0 and everything else is 1. Can I get here? Now, obviously, if this was 1, I cannot do it. I have already told that. But if this was 0 and everything else was 1, can I do it? Well, I can. How? First of all, I will use, so I'm gonna describe the operations in the reverse order. So I can make this 1 using this, right? And then this one using this. Notice that I can use this because this will be overlapped in the next operation anyways, so I don't care. So that's why we are going from reverse. So I keep doing this like this, and then for this I can do an operation like this, for this, this. So I can always keep doing this, and I'll be able to do every operation and make everything equals to 1. So all I needed is 1 0 at the top left. So if it is there, I can always reach any state. And so yeah, we just have to consider operations in reverse. Another good thing that considering operations in reverse does for us is that when I use something, so let's say I use this to make it 1, because I'm considering operations in reverse, I can use this as well in the next operation, because it will get overlapped in the actual order of operations. So let's have a look at the implementation. So implementation is, obviously I go from top left. For 0 I do not care. Now every time I encounter a black, or sorry, 1, yeah, that is black only. So every time I encounter a 1, what I do is I try to see its left and top. So using dx and dy, I am able to iterate on the left and top, and if either of them is 0, then I can do it. And so I add to my answer. I am making a struct operation for I1, J1, I2, J2 for the subrectangles. I add to my answer and then I make it 0. Why? Because it kind of behaves like a 0 now, because I can use it for my next operation and it won't be affected because it will be overwritten the next time. And if I cannot do it, then return -1. Now, because I have calculated operations in reverse them and then just print them. So that was problem C. Now let's try problem D. Okay, so this was a good problem. Okay, yes. Okay, so we are given two numbers x and d, And a number is good if it is so a number n is good if it is divisible by d, and it is beautiful if it is good and it cannot be represented as a product of two good numbers. So what is a good number? A good number is tx, right? So a beautiful number would not be of this form, right? So x and y are any integers, any positive integers, so it won't be of this form, so it won't be of this form. Hence a beautiful number is not uh, divisible by 0, not divisible by d square. So okay, we have simplified expression for good and beautiful numbers. Now let's move forward. Given a good number, so we are given a good number, so x is d times, let's say, some k value. I want to know if it can be represented in at least two different ways as product of beautiful numbers. So I want to, so k can be anything, right? K can also be a multiple of d because it is just good, it is not beautiful. Now I want to represent it as product of beautiful numbers, so d times some value k1, right? But k1 is not a good number, otherwise it won't be beautiful. And similarly k2. So I want to represent it as product of some beautiful numbers, and it should be possible that I can have two different type of ways to show it. So for example, uh, I had like, okay, so if x was 1000 and d was 10, then one was to have 10 times 2 and 10 times 5. So this is one way to represent it. So notice this is a beautiful number, this is a beautiful number, and the other way is 10 times 10 times 1, 10 times 1, and 10 times 1. So I have three beautiful numbers, and since there are two different ways because the numbers occurring in them are different, it is eligible to print yes. Okay, so now that everything is clear, I just want to tell if I have to print yes or no. So let's see. Let's try to divide k by d as many times as possible. So let's say this becomes d to the power some p and then k dash. So now the final product can look something like d, so p times, and then k dash can go some anywhere, any in any of these numbers, right? Now if k dash is not prime, so it is at least a times b, where a and b are prime, right? If it is at least of this form, what I can do is, in one way I can give a here and b over here. Now also notice that for this I need at least p to be equals to 2, and then in the next way what I can do is give ab, that is entire k dash here, and d here. So if k dash is not a prime number, then I can always get it, right? So see, one thing I forgot to mention is that p needs to always be greater than equals to 2, because if p is not greater than equals to 2, I will only get one beautiful number, and I cannot arrange or factorize or whatever one number into multiple ways. One number is just one number. So this is a required condition from now on. So after dividing k as many times as possible by d, I got this form, d to the power p k dash, where k dash is not a good number. Now the final configuration that I can have is like all the d's, so all these beautiful numbers, and then one time I can factorize it like a times b, give a to one number and b to another, and the next time I can give ab to the one number. So if k dash is not prime, so if it is not prime, then I can get it. get at least two configurations. So answer is yes. So let me just erase this. So I had x is equals to d to the power p k dash, and one condition is if k dash is not a prime, then always true. Now let's take another number. So now let's take the case where k is prime. So if k is prime, then I can distribute k to only one of them. So k goes here, k dash I mean. Now k dash is here, and no matter which one I give, it's the same thing, right? Because the set of the numbers that I'm using is same, so configuration is same. So how can I get another configuration? Well, if one of these d, right, is not prime, so if it is not prime, if it is of form AB, then what I can do is transfer A here and transfer B to another. So I needed 1, 2, at least 3. So if there are at least 3, so if P is at least greater than equals to 3 and D was not a prime number, so D is also not a prime number. Now I'm considering for k equals to prime, right? So now if k is prime, then if P is greater than equals to 3 and D is not a prime, then what? Then obviously I can always get a good I can always get two configurations. One time A went here, B went here, and the next time B goes to the other one, A goes to the other one. Notice I cannot move entire D, which is A times B, to the one number, because then it will not be beautiful anymore. So that seems to be enough. But if you run that on samples, you will fail, and you will realize that one edge case which was in the sample. So luckily you don't have to use your brain. Now I'll tell you what it is, but so if k was prime, so if k wasn't prime, then I can always get it. If k was prime, in fact it doesn't even matter if k is prime or if it is 1, right? If it is 1, then I can, all that matters is d prime or not. So it doesn't even matter. What matters is d not prime? If it is not prime, then I can distribute a to one of them, b to the other one, and in the next time, so it becomes like dA, dB, and whatever, and then in the next configuration it becomes like this. Sorry, not this. Actually, no. I'm gonna take a retcon here. K dash is prime. Okay, it is not 1. It's a very case analysis problem. That is why I'm messing up here. So one is this and the other is this. Cool. So I get at least two configurations. So if D is not prime, and okay, let me have a look at my solution as well, so that I can take reference. So okay, let me go through the code and explain it case wise, because like I mentioned, it is just case analysis from here on. So not a very fun problem, I'd say. X, so take the input. I have d2 as d square. Like I mentioned, p has to be greater than equals to 2, right? So it should be divisible by d square. If it is not, print no. And now I'm gonna count how many times. Oh, okay, have I failed system test? Okay, I have not failed system test. Whatever. So, and now I'm counting. Basically, what is p? Times is just p. So after I've counted that, right? After I've counted that, I am also calculating the number of factors of number of, so if it is like 8, right, if k is 8, then what I'm calculating is it is 2 to the power 3, maybe it's like 8 times 2, right, 8 times 3. So I'm calculating the sum of these powers, so 4. Now if it is greater than 1, then that means it is not a prime number, and if it is not a prime number, then I can always do it. However, if it was not a prime number, right, so if it was not a prime number, and okay, yeah, times is just p. If I was thinking that times is not p, so I got confused why didn't I pass. Anyways, so if it is not a prime, like I was mentioning, p has to be greater than equals to 3, because to get two different configurations, I need to depend on d now, one of the d's. So now I calculate the count of d, which is again the power of sum of power of factors, and also how many different prime factors it has. So I calculate them, and I have pd, which is the prime, one of the prime factors of it. And now what I'm saying, so this is also part of the calculation. So now if d was something like 2 to the power 3, 3 to the power 2, then count d is 5 and unique d is 2. So sum of the powers, number of unique ones, and pd could be anything 2 or 3. This is pd here. Now after that, okay, after I've gotten some information about it, now like I was mentioning, if so if it is not a prime number, if it is not a prime number, so let's say I have only 3, okay, I'm gonna consider only 3 because for more than 3 it works the same way. If it is not a prime, it is of at least this form. So the two configurations I can get are write them separately and then distribute it one. So I got two different configurations. I don't have to worry about if k dash is prime or if k dash is 1. Okay, so with that I got two configurations, and that is what I'm checking here. If count d is greater than 1, then can equals to true. There was one edge case though, and the edge case, like I mentioned, was in samples. It was this one. The edge case is this one, 128 and 4. Now let me explain the issue. So it is 4, right? So numbers can be 4 4 4, so 4 4 64, sorry, 4 4 16 64 times 2. So I have, so p is 3 and k dash or whatever is 2. Now it is prime number, right? It is a prime number. If it wasn't prime, I would always be able to do it. And this prime number is also equals to the prime, the one and only prime factor of d, and its count is also only 2. So because its count is only 2, right, and also there are only 3 numbers, right, and p is only 3. So in this case what happens is I'm forced to move 2 times 2. So 1 2 goes here and another 2 goes here. So I'm forced to make it like this, 4 times 2 and 4 times 2. And now the other 2, when it goes here, it makes it 4 times 4. And notice this is also d, so this doesn't remain beautiful. So that is why I need to check this special scenario, that if there is only one unique number that is the prime factor of the d, right? So unique d is 1 and p is 3. So p is 3, then count of the unique factor is 2 because it would be forced. If it was 3, then then it was maybe 8, so it could have been like 8 times 4 and 8 times 2, and the other 2 can go here and all is well. Okay, so that is why I want to count d to be exactly 2, and then also remember I saved the prime, one of the prime factors of d. If there was only one prime factor, I have exactly that prime factor, and if that is equals to k, then can is false. So this was the edge case. I'm not entirely sure how is someone supposed to figure this out. I think That is why they added it in sample test cases. Otherwise, we would have seen an ocean of failed system tests, or at least if it wasn't in pre-tests. So yeah, that was the solution for D. The only problem I remotely liked in this contest was C. Let me know your thoughts and make sure to leave a like, subscribe. I'll see you next time and bye.